Analytical Chemistry 1, Lesson 19. Activity is determined by referring to specific standard states that are agreed upon. The reaction quotient is a function of the activity of all reaction participants. This controls changes in a reaction's chemical potential, and if we focus on processes at constant temperature and pressure, changes in the Gibbs function. The challenge is what to do about the activity of each species, especially as it changes throughout the course of a reaction. For solids and pure liquids, it's quite easy. Their activity is always 1. Now remember, that activity is unitless because it is always referenced to some standard state with the same units. Our approximation for solvents make them equally straightforward. As long as solutions are dilute, the solvent is treated like a pure liquid and also has 1 for its activity. The challenge remains with solutes and gases. The activity of solute I is the ratio of its concentration to that of the reference concentration, all modified by the activity coefficient. Commonly, and certainly for our class, we choose the reference concentration to be 1 molar. Hence, if we report concentrations in molarity, the units will cancel and we have the number we used for the reported concentration. But it now has no units. They've canceled out. There's still the activity coefficient, but it too is unitless. So activity of a solute is unitless. But it has the same number as the concentration of the solute when measured in molarity. But what about the activity coefficient? There are many ways to try to estimate and calculate it, but that remains a challenging task. It can be measured experimentally with careful work, but when concentrations are low, the activity coefficient approaches 1. For our work, therefore, we will make the assumption that the activity coefficient is 1. That makes it appear that we will ignore it, but in fact we're just assuming it is always 1. Since the reference condition is also 1, as in 1 molar, we generally do not write it out either. Instead, we generally replace the activity of a solute with its concentration measured in molarity. Later on in your careers, it may be necessary to include activity coefficients and perhaps to use different standard states. But from here on in this class, we will use concentration and molarity when forming a reaction quotient. It's important to remember that while you will enter a number for a species concentration which seems to have units of molarity, and actually you have canceled those units with the standard reference state. They do not contribute any units to the reaction quotient. And what about gases? Well, they have a similar issue as with solutes. That is, their concentration changes and their chemical activity changes as well. One difference is that we measure their pressure rather than concentration. A standard state for pressure is commonly either 1 atmosphere or 1 bar. We will work with 1 atmosphere. Now, there are some other differences in language. You will hear talk of fugacity instead of activity, but the essence is that the same thing happens as with solutes. We take the partial pressure, measured in atmospheres, divide it by a reference standard state of 1 atmosphere, and multiply by a fugacity coefficient to find the activity of the gas. And we make the same approximations. Low partial pressure gives a fugacity coefficient near 1, so we assume it is always 1. The partial pressure in atmospheres has its units cancelled by the standard reference state, which also has the value 1. Therefore, our approximation is to replace the activity of gases with the number that is the partial pressure of that gas measured in atmospheres, but with no units. All activity components, including those within our approximation, are unitless, so Q is unitless. That's as it needs to be because we're going to take its logarithm. But when we write out Q, we insert solutes as a concentration using square brackets, and pressure as their partial pressures. We just leave off the units because we've canceled them with the standard states. Solvents, pure liquids, and solids don't appear explicitly, but not because they're not involved. Rather, it's just that their activity is 1, unity, and so we leave them out to simplify the expression, but don't forget they really are still there. Here are a few examples, and I admit that I don't expect these will seem strange or new to you. We've come back to the way you've generally been taught equilibrium in your earlier courses. Let's look at the reaction between aqueous iodine and HCN. The reaction quotient has this form within our approximations. All participants are aqueous solutes, so they appear as concentration. At any point in the reaction, we can enter the number that is the concentration for each species measured in molarity, and, when all multiplied out, will provide a unitless number that is the value of the reaction quotient at that point in the reaction. We could then use that number for our expression for changes in Gibbs energy to find the current value of delta G. To do this, we would, of course, have had to already calculate the value of delta G naught for this reaction. Do you remember from Chem 1050 that we would use formation data to find that value? Good old products minus reactants. And we must make sure that the table we used was for concentration measured in molarity. Remember that the superscript, either the naught or the Plimsoll mark, means the value measured for the standard state. The standard state for this calculation must be the same one we are dividing the measured concentration of pressures by. But if we had that data, then a calculation of delta G for this point in the reaction would tell us whether the reaction would continue in the forward direction, delta G being negative, proceed in the reverse direction, delta G being positive, or be finally at its equilibrium condition, delta G equal to 0. And remember, delta G naught is a constant for any given reaction at the temperature being considered, while delta G is continually changing throughout the course of the reaction. It is always moving towards a minimum in the Gibbs function, which will occur where delta G equals 0. Now, do not forget that we have made approximations to get to this point. Specifically, we are assuming that the activity coefficients for each species involved is always 1. We hope that they will be close to 1, but there will be differences. However, for our course, we need to not get bogged down in calculations for activity so we can more fully explore the chemistry involved. And so we make this approximation. Here's another reaction, the reaction of solid phosphorus with chlorine gas to form a liquid phosphorus trichloride. What is Q for this reaction? Note that phosphorus is in the solid state, and PCl3 is a liquid, not dissolved in a solvent. So both of these show up with an activity of 1. Within our approximation, the activity of the chlorine gas is its partial pressure measured in atmospheres. So Q in terms of activity would have this form, but within our approximation it is just the reciprocal of the partial pressure of chlorine measured in atmospheres raised to the 6th power. We don't explicitly include the solid or the liquid, not because they're not there, but because they have the constant value of 1 throughout the reaction, as long as there's some of it present. But why do we need to raise the chlorine pressure to the 6th power? Remember where the form of Q comes from. The chemical potential has a logarithmic relationship to the activity. But PCl3 appears 4 times in this equation as written, while chlorine appears 6 times. So we multiply each by that coefficient. And when we bring the coefficient into the logarithmic argument, it becomes an exponent. Put it all together, and there is our expression for Q. And here is another one, the simple dissolution of zinc metal in an acidic environment. Hydrogen gas bubbles off. We will use concentration for the aqueous solutes, pressure for the gas, and the solid will not appear explicitly, though we will remember that it is present as the number 1. Note that the hydronium ion concentration is squared since its coefficient in the reaction equation is 2. All of these equations and calculations depend upon how we choose to write the reaction equation. Now, the actual interaction of atoms and molecules does not care how we write things, but we get to choose how we will analyze the reaction, and we do so by the coefficients we choose. For this reaction, delta G naught equals minus 147.2 kilojoules per mole of reaction events, and Q would have the form given here. But we could have written this equation like this. Now, it's still balanced, but now delta G naught is only half of what we used before, namely minus 73.62 kilojoules per mole of reaction events, as it's now written. And now Q would take on a new form. Our interpretation of the reaction does not change. If we were to find conditions that suggest the reaction is going to continue moving forward, then we would reach that same conclusion with both forms of the reaction equation. Remember that the phrase per mole here is referring to the reaction events, per mole of reaction events, and it's not speaking of any particular reaction participant.